let's get you on, Jason. Jason, can you do me a favor and just introduce yourself? And most people know you, but if we can just get you to give us a bit of an introduction and set the scene, that'd be fantastic.
No problems at all. So firstly, can you see my slide?
Yes.
Excellent. That's a good start. So Jason Cotton, I'm the Program Director of the Intelligent Water Networks here in Victoria. Our membership is all of the urban water corporations in Victoria, and we also have Tas Water as a member, an associate member of IWN, as well as the Department of Energy, Environment and Climate Action, or DECA, as we love to call them here, which is the previous DELP. Anyway, I'll get a bit more into that as we go through the presentation. Now, Alicia gave me 10 minutes, and as Rodrigo will attest to, who knows me well, I talk underwater with a mouthful of marbles. So I will try as much as I can to stick to my 10 minutes, and please stop me in full flight if I go over time. So hopefully that slide has changed, and it says, who is IWN? Excellent, we have a plan. So IWN is a member-based program of Vic Water. Vic Water is the peak body for water in Victoria. Victoria has a unique structure to the water sector here. We have 18 government-owned water corporations. It's very different to South Australia, that's predominantly got one water corporation. Western Australia's got one. New South Wales has got one large, one medium, and 93 councils, and so on. So we all have similar challenges in terms of those 18 water corporations. And what was happening, because they are all independent, there can be duplication of effort and funding and working on solutions to those same problems. So 15 years ago, out of Water for Victoria, which is the water plan for Victoria, IWM was stood up, and its role was to really drive innovation into the sector and the adoption of new technology as a way of presenting potential solutions to the challenges that the sector faces. And as I said, we've got all of the urban water corporations and DECA as our member, plus Tas Water. Our purpose is to really, as I said, to be a catalyst for transformation. So the adoption of technology and innovation is fantastic, but what's the means to the end? And the end is really about industry transformation. We've got these incredible challenges that are before us, and it's a way of rising to those challenges by employing different ways of thinking and innovative thinking. We also have, interestingly, an emerging leadership program, which is emerging leaders from across the sector. So we call that our Champions program. And we take them through a formal program of experiential learning. And it's really about how to lead innovation and change within their organisations. We're very clear about where we play. We don't do R&D. We participate in research and development projects for sure, such as the Smart Creek CRC. But our role is to participate from an in-kind perspective to guide the direction of research and provide knowledge, industry knowledge into the direction of research. But once there's an outcome from that research, our role is very clear. We play significantly in the space of translating the outcome of that research into industry application. Now, to do that, we have 12 programs of work. And our programs of work cover everything from contaminants of concern to assets to pipeline to digital metering and as Rodrigo said, circular economy and so on. Where we are with this Smart Creek CRC is, as we've circled here, is in pipeline intelligence and asset management. It's about how do we build intelligence into our assets so that we can manage our assets more effectively and more efficiently. That broader diagram just shows you our structure. We are a part of Vic Water. I report to the CEO of Vic Water. Our governing body is the Vic Water Board. Our program governing body, we have an IWN executive, which is senior leaders and MDs from across our membership to help to bring in that direction, that strategic direction on our program. IWN has 2 full-time staff, myself and a deputy program director. Everyone else is a volunteer from the sector. And so we have about over 100 volunteers from the sector who form the working groups and leads of each of those programs. Anyway, that's enough about IWN. Let's get into the meat. Why are we here? What is the problem that we're trying to solve? This is a typical sewer. As you can see, that's not how that sewer looked the day that it was installed. There is a significant amount of corrosion and concrete degradation that is occurring in that sewer. Many years ago, we used to send people down in there to do the inspections. These days, we send robot cameras. One of the things that I'm really interested in is how can we enhance robotics? How can we build in artificial intelligence and machine learning into the use of robotics in our sewers so that we can not only assess the condition of the sewer, but predict the condition that that sewer is going to be in, and hopefully any challenges that are presented from the conditions of that sewer are actually overcome. So how can we prevent the sewer from doing that and corroding? Why does it corrode? Why do we get this degradation? Well, you'll probably know the old rotten egg gas that used to make in the labs at school or at university. That's hydrogen sulfide, and that smell is characteristic of the odor of a sewer. However, that compound is problematic, not just from an odor perspective, but when that goes into the headspace of the sewer, there are these bacteria that live in the pores of the concrete up in the crown of the sewer. And because the water line is not the only part way up the sewer, you do get oxygen. And so that hydrogen sulfide gets absorbed into the concrete. These oxidizing bacteria then have a field day with the hydrogen sulfide, and it forms sulfuric acid. And it's that sulfuric acid that eats away at the sewer. And so that is a wicked problem. The other side to this wicked problem is that you put sensors in there, they don't last very long. And so trying to measure this degradation, trying to measure the hydrogen sulfide content is entirely problematic. And so that's why we're here. We're here to solve that problem. So as you can see, here's a close-up of the sewer, and you can see that concrete degradation seeping into the concrete layer. And so you get this layer. So the way that we tackle this right now is we have a sacrificial layer of concrete in the sewer. We actually, resign ourselves to the fact it's going to corrode, and so we basically put a sacrificial layer of concrete in it, so that the sewer lasts a bit longer. So you can see here that as you get this porous degradation and that falls away, you then get the second layer where it starts to degrade because the sulfide migration is occurring in that concrete. And that is not a good thing, because what that leads to is sewer collapse. Now, you can imagine the network of sewer that's underground. And if you start getting collapses of sewers under roads, under runways in airports, under houses, that's a massive issue. And so we want to solve for this problem. The other side to this problem, and this is where we're focusing with Smartcrete, is that along the network, obviously these maintenance holes, they are a natural area where there's a lot of headspace and air, and the hydrogen sulfide gas goes into that headspace. And so we get significant degradation of these maintenance holes. And of course, this is where trucks drive over, people walk over, etc. So you get a truck driving over that, as you can see there, that's going to collapse pretty quickly. And so the trials that we're doing with Smartcrete, which Alex will talk into a little bit later, is that we're looking at a whole variety of different robotics of how to do measurements in that particular space that are non-destructive. And we can get a condition assessment and indication of that sewer. And so, as I said, the challenge is in that headspace to develop devices that won't also corrode. And that's a delicious problem. So I think my 10 minutes is just about up. I've done well. I will hand over to Alex to talk about how we are partnering through the CRC to develop these solutions. So thanks everyone for listening. And I think we're going to take questions at the end. So I'll stay on the line. Cheers.
Alex, you'll have to unmute yourself.
Yeah, Alex, you're on mute.
Thank you. You'd think you'd get used to it these days.
Yeah. Alex, can you just do a bit of an introduction of yourself, a background,
Yeah.
just a bit about the project and launch it? Thanks, buddy.
Yeah, no worries. So, yeah, my name's Alex. I'm from the engineering department at Trobe University. I have a pretty keen interest in robotics, field robotics, and have been trying to tackle this wicked problem for a few years now. A colleague of mine, Robert Ross, is also, we work together a lot in this space. So over the years, we've developed a few different robotic solutions, and then we're partnering with our existing partners with IWN and Southeast Water to develop I guess the next phase of these robotic solutions. So overall, we have 2 projects that have been funded through SmartCrete. One is focusing on the sewer access points, and the other one is focusing on the sewer pipes themselves. So similar use cases in that we're trying to determine the degradation and look at the remaining life and how we can extend the life of these assets, but different application in terms of the robotics and how we get down there. And I'll talk a little bit about that in the slides ahead. So I'll just share my screen, assuming that's coming up.
Coming up fine, thank you.
Beautiful. Okay, cool. So lots of concrete sewer pipe in Australia and New Zealand. So there's, I'm not sure exactly where I got this figure from, but it's about 300,000 kilometres of concrete sewer pipe. So it's a significant asset that Australia has. It's been listed as one of the federal government priority areas too, in terms of infrastructure and trying to maintain and prolong the life of this significant amount of infrastructure that's around Australia. So, as Jason spoke about before, there's a common failure mode, which is the H2S attack. It's it can be quite prevalent in certain parts of the sewer network, and it varies along different areas. So you'll find some areas might have lots of H2S issues, and some areas are untouched, and they can remain in the ground for many tens of years, maybe hundreds of years in some of the really old sewer pipes that we have, in particular in Melbourne. So a bit of a background to both projects is how do we go about improving the remedial works, how do we prolong the life of these assets? The current standard to do this is using, as Jason spoke about, CCTV. So essentially we put a camera down the pipe and we have someone watching a screen assessing what they perceive as the condition of the pipe. And so there's a code, there's a water, I forget what the acronym is for, what it stands for, WSAA. They have a code which I guess buckets the condition of the pipe into one of 5 categories. So I think it's 1 being the best and 5 being, you need to replace it as soon as possible, otherwise it will be an issue. Now, what industry has found is that classifying of the sewer pipes is prone to human error. So you obviously got a person watching this this footage going down, and they might get a little bit of training, but the outcome is that they incorrectly classify the condition of the pipe, which then can cause some collapses and some quite catastrophic and costly damage. So we're tackling this from how do we improve from where we are using this, the CCTV methods, to something that's a little bit more informed in terms of sensing technology and robotics. Okay, and how do we quantify more accurately what the condition of the pipe is. Okay. And that is, the current state of the pipe, but then also what is the degradation? What is it looking like going forward, to give a sense as to what the lifetime might actually be. In doing this too, you want to minimise the risk of cost and risk. So we obviously don't want to send people down pipes anymore. We want to use robots and sensors to do this work for us. So it gives you a bit of background. Just to give a little bit of an overview as to what, and this might be somewhat obvious for some in the session today, but it's good just to clarify what we're talking about here. So the sewer access points are obviously the hole that goes down from the surface level down to the sewer pipes, and they have sort of a funny shape, well, not a funny shape, but a shape to them that makes it challenging, obviously, for a robot to do a condition assessment in. So there are certain sort of physical constraints as to how we may position a robot in this pipe to do our sensing. And then you've got your sewer pipes, which are obviously the pipes that go in between the sewer access points. So to get there, we have to obviously traverse the sewer access point. We pop the robot down, and then it will go down along the sewer pipe, do its condition assessment. Or in this case, I've got an image of a CCTV robot. They call this robot the Beast. I don't know why. Maybe it's a bigger robot or something, but it's got this nickname, the Beast, which is good because it actually pushed our prototype robot down the pipe when we were doing some field trials about a year or two ago. So in terms of looking to the right of the screen, stuff that we're particularly interested in terms of getting a sense of what the condition of the pipe is. One is the internal diameter. And so obviously as the concrete pipe degrades, the internal diameter will change. And we're talking about the effective internal diameter, not the the internal diameter to the sound concrete. So that's something that we're particularly interested in, something we've looked at over the last few years, but there's obviously other aspects to the concrete pipe that we would like to understand. One of them being the external diameter. Now, it might not be obvious, but for older pipes within a sewer network, and this is particularly the case with people that we've worked in Victoria, but I'm sure this is a nationwide problem. For those pipes that are, 1960s, 70s, that sort of vintage, those pipes were whatever they had in the yard. They went in the ground. So it's unknown as to what actually is in the ground. The historical records of what is in the ground is unknown. But so that poses a problem because we don't know where we're starting from. And so we need to take somehow, using a combination of sensors, to measure that external diameter so we can get a sense of a snapshot of what actually is in the ground. So that's why we're particularly interested in the external diameter. Some other nomenclature is like the obvert and the invert. So when we're talking about that, that's the top of the pipe, and should be an arrow to the top here, it's missing, and the invert, and then obviously the effluent that runs down the pipe. Now, in terms of degradation for a sewer pipe, it varies. Okay, so some people think that there's more degradation at the obvert. Some people think there's more degradation at the effluent line. But from what we've found, and we haven't done a lot of testing, we are under the impression that it varies. Okay, which makes sense, right? Because it's very dependent on the local environmental conditions as to how much degradation you're going to find on in a particular section of pipe. Okay. So I'll move on to, just to give a little bit more of an overview of concrete pipes, and I'm sorry if this is common knowledge, but it might not be for some. I've lifted this out of the Wholesome concrete pipe reference. So obviously these pipes, they're made to a particular standard, modern standard, Australian standard in terms of concrete compressive strength, all that sort of thing. When we're talking about pipes, they're classified into different classes and different DIN sizes. So for our projects, we have focused on smaller diameter pipes, but for the ones that with Smartcrete, we're looking at diameters typically 600 and above. So for a manhole, sorry, I shouldn't say that, sewer access point, the opening size is usually 600 mil, and then it will fan out to a much larger diameter. So that's kind of what the sort of sizes of pipes that we're interested in. And then different classes have different internal diameters that they may start off with. So one of the things that we will do with this project is also to determine which class of pipe is in the ground using our sensing means. Okay. Now, this is also, so on the right-hand side, I've got a little bit of an image as to what, how we currently tackle this problem and we simply just add in sacrificial layers as Jason was talking about. So extra cover up to 25 mil is usually added and that is to ensure that we don't obviously impact the structural integrity of the pipe, but we also want to make sure that we don't expose the rebar. So as soon as the rebar is exposed, that's a pretty critical issue that we must deal with. So yeah, that's why we add material to the inside of the pipe. Another way that this problem's tackled is to add in a high-density polyethylene liner, and that can be added either before installation, or it can be added post. So if you've got a pipe that's got some issues, you can run a liner down there to protect or to extend the lifetime of the pipe. How am I going for time? I probably should kick on here because I reckon I'm going to run over 10 minutes. So
keep going, Alex.
Keep going. Okay, all right. Just you keep me in check, just so I don't run over time. So sewer access point. This is kind of
5 minutes.
5 minutes. Excellent. All right. Yep, I can do that. So this is what a sewer access point typically looks like. So you'll have the access hole, which is normally 600 mil diameter, and that section of the pipe will only be a short sort of section typically. The reason is that if someone's going to enter into the hole, they don't want to be sort of confined within a 600 mil opening. So they try and make this as small as possible, and then the pipe will extend outwards to typically a metre, around a metre, maybe 1200 on some of the larger sections. So it does vary. Again, for those older pipes, it depends how they did. If they cast it in situ, so they've got the concrete truck and they had formwork and they made the pipe. For modern installations, it's pre-made, prefabbed, and they drop it in the hole, and you've got the pipe there ready to go. So in the hole, especially for the older pipes, we have ladder rungs. These, depending on the water authorities, have been removed. There's sort of two schools of thoughts there in terms of if the ladder rungs need to be removed or not. Essentially, if someone needs to go inside the pipe, one school of thought is that you could use the ladder rungs to get out in an emergency. The other school of thought is that these ladder rungs get in the way because you've got somebody harnessed up that they drop down into the hole. For us, because we're the robot guys, the ladder rungs can be problematic, especially if some of the ladder rungs come up into this 600 mil opening, which gives us less space to get the robot down into the pipe. So we would prefer obviously if the ladder rungs were gone, but it is something that we need to deal with this. So the reason I'm sort of talking about this in particular is that it sort of gives you an overview as to what the geometry and what we're dealing with in terms of a sewer access point in particular. It's not a standard straight pipe. It's got some bits and pieces that we've got to deal with. So at the moment, how do we measure the degradation? And 2 minutes, okay, I'll go through this quickly. We use a penetration test effectively. So what we mean by a penetration test is that we have a little probe that comes out and it touches the wall and it will push through till it gets to a certain threshold. Where in the past we've set that to about 50 newtons, so it's not very high threshold. And with that we can see what is the depth of penetration, where does the start of the sound concrete begin, and we're not really greatly impacting that sacrificial layer as well. Oh, so that's not sacrificial layer, the degraded layer, I should say. Okay. Why is my thing not going forward? Oh. Oh, I want the other picture. Oh, I can show this. Yeah, so this is what a penetration test looks like. So, non-degraded, we've got the penetration distance on the bottom and the load on the top. Sorry, on the y-axis, going up to a 50 Newton threshold. So for non-degraded, you expect the force to ramp up very quickly. For degraded concrete, we have this much longer sort of profile that we find. So this is this was a project with IWN many years ago to look at the sewer access point. So this was a proof of concept, just to have a look at this penetration test. So this was had a penetration thing on the end, and it connected up to an app, which we could get that information out. This is another one. This is 3 ppr plus. It's a robot that does the sewer pipe. So we put this down the manhole, the sewer access point, and it goes along the sewer and does a similar thing to does a penetration test. So yeah, you can see it here getting lowered into the hole. You can see our issues with the ladder rung. And that we need to think about how we get that robot in there. I'll quickly go through this. This is it in the hole doing some penetration tests. I won't show the video because I'm assuming. Yeah, I'll just keep going through. There we go. That one's got a bit of stuff on the end, so and yeah, this is a good one. You can kind of see that I hope if that video is coming through, that we can test at all different angles within the pipe. And so this resulted in some data that showed that the penetration distance does vary along the length of the pipe and at different angles. And again, here we're looking at classifying the pipe in terms of which class. So obviously, yeah, as the effective internal diameter changes, we have different types of classes along the length of the pipe. So where do we want to go from here? And this is where the SmartCrete projects are picking up from, is we want to build on the penetration test, but look at multi-sensor application. So we want to look at different types of sensors and different types of things to classify, to improve our understanding much further than what we were doing with just the simple penetration test. And it all comes back to those parameters that I showed with the sewer pipe. So, you know, external diameter, internal diameter, rebar cover, compressive strength, all of those sort of things. There's some of the key parameters, but there's other parameters too, you know, pH level, moisture, those sort of things. So, yeah, we're looking at a multimodal sensor package that we can position with our robots in the pipe to get a much better understanding and to improve on the current classification methods. And I think that's it. I've run over time and I do apologise. I got excited.
I think we all did. I should have done this before, but sorry, guys. The other person that's on the line that we should sort of acknowledge is Professor Vutserevivatnanon, who's a research director of Smartcrete, and he and I have spent many hours looking at concrete pipes and durability and all the stuff that you're talking about and things like that. So rather than sort of start talking myself because I got 1,000 questions, I think perhaps the best way to do this is, look, if people want to ask a question, please chime in. Otherwise, you'll be listening to me and Woot for the rest of the afternoon, and that's not a good thing. So jump in wherever you want, guys. Just if you want to ask Jason or Alex a question, please feel free. Anyone? I know there's been some on the chat. I think Greg, you actually had something there.
Yeah, I can add in Dax.
Yeah.
So Alex, yeah, good presentation. Really nice the way you're working on that. A couple of comments. So yeah, there's been an amount of work done on the key parameters that affect sewer corrosion through a project called SCORE, Sewer Corrosion and Odour Research. I've just posted where that link is, but yeah, humidity is the biggest contributor by far, but you're doing some great work. I'm really interested in just understanding a little bit more about this multimodal probes, which is great. Are you looking at sonar or some way of looking at depth of concrete? Because the key issue we see is trying to understand where a fault is difficult, because it's not consistent along the length of the pipe. It is worse in certain areas, and so how do you identify the weakest area? And so you're looking at sonar and other things to travel along, then test it with your pressure test, that type of thing. Just interested in your ideas.
Yeah. So at the moment, our current thinking is that we would mount that to the robot itself. So it would go in and do I guess a point measurement in the pipe in the different locations. Yeah, we're not looking for voids or anything like that. It's more about getting that external diameter measurement. And the other approach that we're looking at is then feeding that into an FEA model. So if you grab all of these parameters and you feed it into an FEA model, then you can get a good, and considering also the environment that the pipe is in, whether it's clay or sand or rock or what have you, can give you a bit more of I guess a localized understanding as to what the current state of the pipe is in terms of its structural integrity and that sort of thing.
So we ran some trials, Greg, Greater Western Water in December of last year, in sort of shaping up the next phase of trials with different devices. So we have this robot, and we were strapping different devices to this robot. So we used ultrasound, we used ground penetrating radar, we used a hammer test to look at vibrations. We did the penetrometer, so we looked at the penetration test, and I think there was one other that escapes me at the moment. So we are looking at a broad suite of different testing methodologies and different technologies that we could potentially put on this robot to get a whole raft of different data. But that was the first trial. We learned a lot. It turned out the sewer was built so well that it was built like a brick outhouse, and so we need to go and find a sewer that's been a little bit more compromised. So shout out to Greater Western Water. Back in the day, they built their sewers pretty well by the look of it. So we are looking for one that's a bit more compromised that we could do this work. And the team on the research project are redesigning some elements of that particular robot to accommodate these devices. So very early days as yet, but the scope is to look at a bunch of different technologies.
That's brilliant.
Okay.
Just one second question would be, how long? What's the timing, do you think, before we'll have something, results?
Yeah, great question. It's a PhD study, so there is a PhD student working on it. So let's say 3 years.
Okay,
Yeah,
Yu Chin, can I bring you in here because you had a question as well, or you had a comment in the chat in relation to concrete cover and reinforcement. Please fire away.
Yeah, thank you. Alex, just would like to see your opinion and comment on this, because on the AS4058 they status that the NIP of at the end of the reinforcement can be exposure without the concrete cover. But based on your research, just now you showed a couple of photos, some the corrosion is very badly. What do you think about that? Because the NIP or end of the socket of the pipe, the reinforcement can be exposure. What do you think about that? Thanks.
Yeah, I'll be honest with you. Yeah, I'm more of on the robotics and sensing side. So the the actual concrete in we actually have another academic who's providing that input. But
And who's that, Alex?
that's Vipul Patel. Yeah. But maybe Jason, do you have an idea of this from your industry experience?
Yeah, it's not really my field of expertise. I'm more into the chemistry side of the sewer itself rather than the concrete. So yeah, I can't really comment.
This is an absolutely wonderful area that I can bring Voot in. Voot, you know a little bit about concrete over the last 40
Beautiful.
years. What do you reckon? Yes, look at how I dropped him in it.
Well, Dak, I'm afraid I haven't looked at the joint. I guess the issues really. What we have done at UTS is basically done the finite element analysis to basically work out the stress distribution, the influence of reinforcement or pipe without reinforcement on the stress and the deterioration of the concrete pipe, which I'm already want to share with the La Trobe University team already. But Eugene, I do not have any particular contribution to that question. Sorry.
Thanks.
Okay, moving along, Subhra, you have a question about penetration values and taken on aggregates, whereas compared to where you take them on paste regions and things like that. Subhra, did you want to just articulate a question? Maybe we can have a discussion on that.
Thanks, Daksha. My main concern, but first of all, nice presentation, Alex and Jason. So my question was, the method works on penetration value. So I presume the load, I think the presentation load versus displacement profile was presented. So the load versus displacement profile may vary for the same state of concrete if the measurement was taken directly on the aggregate, maybe on the paste region, maybe in the interface. So are you doing some kind of an averaging method to look into account, or what's happening?
Yes, yeah, absolutely. No, 100%. Yeah, there is definitely a difference between hitting aggregate versus I guess the mortar and stuff around it, or whatever composite material it might be. So one way we're looking around this is to actually have a movable penetrometer. So it's on a rotating disc that will, in a certain area, get an average as to what the penetration distance actually is. So yeah, you know, the key bit of information that we want to understand is where is the sound concrete? Where does that start? And so, yeah, you can get erroneous readings if you hit an aggregate. With the 3PR robot, the robot arm actually was able to move just ever so slightly. So if it did have a glancing strike on a bit of aggregate, it actually would move just a little bit to get to the point where, yeah, just to get a bit more of an accurate reading. So yeah, no, it's a valid, definitely a valid thing that we're looking at in this project.
Thank you for that. Any other questions from anyone in relation to this? I have to sort of put in my 2 cents worth. Jason, Alex, this is an absolutely fascinating project. I've spent my years working with Voot and then working with what is now Holcim. I used to work in Humes, and I've been a supplier of these types of materials. And there, I recall of a colleague of mine from Humes, the wonderful Dr. Norwood Harrison, who actually was a guru in terms of how pipes worked and all the issues that you're talking about. And you're absolutely right. The actual getting in there and getting data, because at least you guys are now starting to get data, and it's all about trying to get the best out of the infrastructure, to the assets, to try and make them last as long. But you do have some challenges, and the challenges are, well, once you get over the fact that you've got the robot going in, then you've got those wonderful tests that you can do. Now, the fact is, I'm not even aware, but the fact that you can actually go in there and get these tests is actually really important. The thing that I'm finding really interesting, and I'd be interested in your comments, is that the pipes are generally done to an Australian standard AS4058. AS4058, when you look at durability, calls for an absorption test. And I remember Voot and I mean, we've been looking at this absorption test, and it was done back in the 60s, and it's a way of doing quality control on the pipe. But what that absorption test does versus the sorts of stuff that you guys are doing in terms of how the thing is working and things like that, it's really interesting, because as with all tests, and even in the list that you mentioned, your penetrometer, the challenge is not only to get a sensible reading, but then what does that reading mean in terms of the sort of stuff you guys were talking about in terms of your finite element modeling, and how long this thing is going to last, and what do you need to do, and all of this sort of stuff. So I'm absolutely encouraged. The thing, though, is that I am assuming, and I'd be interested in your comment. We use a spinning method, like most of the suppliers use a spinning method. I think it's Humes and Civilmart now, which is the old Rockler, and they're changing from that to a vertical cast system. And the pipe quality is actually really good. But then, as you say, you've got this issue of hydrogen sulfide, and if you've got high levels of acid, there's nothing you can do in terms of the concrete can be as good as possible. Then you're going to get these sorts of issues. But I guess that is the failure that you're seeing in a particular sort of age bracket? Are you in your assets as you go through and look at all of these things? Are they recent? Are they earlier? I remember, Jason, you're talking about some of the earlier pipes and things like that. Just where is this problem? Is it just indiscriminate?
Jason, you want to answer that one?
Yeah, it's everywhere, really. There are some old pipes out there that are in pristine condition. There are some new pipes that are not. There are some old pipes that are in very poor condition. There are some new pipes that are in poor condition. It's really about where you get these anaerobic zones, if you like, that creates high levels of H2S. It's also depending upon the nature of the sewage. So, lots of sulfate or proteinaceous materials where there's sulfur content that the bacteria have a field day on and create H2S in the anaerobic conditions. So there's a complexity of factors at play with respect to sewer corrosion. It's not just down to the nature of the concrete, it's down to the nature of the sewage itself. Is it rising? Is it falling? So I think Greg's going to chime in here with a few things. So yeah, over to you, Greg.
Fully support you, Jason. That's exactly, so that sewer corrosion odor project I was mentioning, that's what they did, was trying to understand what were the causative factors, and it's related to your humidity, your sulfide levels, your sewer source. The ventilation is really important. Good ventilation takes out the moisture and the H2S, and that really prevents the corrosion or minimizes corrosion. It's the water, the depth of sewage. There's a ton of stuff here. So it's really hard. You can predict it, but it requires very fine modeling, really hard to do. And so that's why we need to do this testing.
Yeah, I've been in this game since the 90s. That's how old I am. I was part of the move to iron salts with Sydney Water back in that period, where we would add ferrous and ferric chloride to the sewers to knock out the dissolved sulfides to prevent the H2S from sort of forming in the crown layer. And then obviously if you knock that out, you're preventing sulfuric acid as well. But, that's not a cheap way of doing things.
No.
Lots of infrastructure.
Yeah, in the pipes that you guys are looking at, I mean, is there a lot of like those that HDPE that one of you fellows was talking about? Do they use a lot of that in this? Because sometimes there's nothing you can do with the sewer; it's just going to be there.
You just line it, line it with HDPE or something like that.
Yeah, and how good is that? Does that work?
Yeah, it does work. It's less porous, obviously, than concrete, so you're not going to get the H2S isn't going to necessarily absorb into the concrete. So yes, it does work, but again, it's expense.
Yes, it is expensive. Absolutely,
it's an expensive way of going. You think about, what was it, 300,000 kilometres of sewer pipe. Let's line all that with plastic, and then it's plastic. So
it's going to degrade.
It's not just going to degrade. You'll end up with microplastics in your outfall.
Yes.
And so you're basically swallowing the spider to catch the fly.
Yeah. Good.
Just a question to Jason. I heard some time ago that Rockla was developing concrete pipe from geopolymer concrete.
Yes.
Do you hear much of that, and where is that at the moment?
Yeah. There's actually a whole project at play at the moment around alternatives to cement in concrete, so geopolymer, even biochar, for example, and that's another project that we're involved with. The thrust of that project is more around Scope 3 emissions and reducing the carbon footprint of the concrete, but we are looking at geopolymer. So again, the complexity of having to do stress tests, and Greg may have some more insights as to what WAS has done around the standards and applicability of such concretes in our industry. But we're looking at a bunch of different materials, not just from a corrosion perspective, but from an environmental and carbon footprint perspective as well. So there are moves afoot around alternative materials.
In this infrastructure, do we have, like, I know, for example, the bridge guys go out there and look at their bridges and they're fairly sophisticated, whereas when I look at buildings, they're not so. With sewer infrastructure, is there, like, is there any strategy around maintenance? Greg, Jason, Alex, if you know of, like, how do people go around managing this infrastructure? Is it
usually with CCTV footage, so they'll put it.
But is there a plan? Like, we have, for example, in our bridge standard that, the bridge will last with appropriate maintenance or some bloody word like that, and they don't define appropriate and they don't define maintenance, but they do have systems by which they go back every 10 years and the sorts of tools that you guys are developing are exactly the sorts of things that you would need as a first base to do anything like that. But is there a sort of an ethos in the industry where these are pretty important bloody assets?
Definitely, yeah, they are very important assets, and as you saw from the photographs, the consequences can be catastrophic depending upon where the collapse occurs. So there are assessment programs. water authorities, certainly members of IWN, have got assessment programs. There is a program of CCTV footage and assessing the sewers on a frequent basis. So there is a frequency.
And most of the infrastructure is concrete, or are there other materials like
there are
steel?
other materials. There are other materials. So there is the use of high density polyethylene in some sewers. They're generally the smaller lines, and the larger lines will be concrete. So yeah, there is programs of assessment, but as Alex said, it is someone's job 8 hours a day to review CCTV footage of sewers. It certainly wasn't the thing that I aspired to do when I was 5 years old, and so we are looking at technologies that use AI and ML to assess that CCTV footage, to then take that 8 hours and bring it down to 2 minutes of interest. That your highly qualified engineer can then go and look at that and make a further assessment of that interesting footage. So there's multiple dimensions to to this issue. So,
and where are you guys at on this project? You've got a couple of students working. Obviously, you're in the thrust of the research. Are you looking at starting to get some data and publish some information? And
yes, is the answer to that question. This has been a project that's been in play for a while. We struggled to get a PhD student because COVID and international students and all of that.
Yes.
We now have that student, and so we are actively doing field trials. We're shaping one up as we speak. So the second round of field trials with Greater Western Water. Okay. And we'll continue on a program of work around that and generating data and generating approaches based on that data.
Fantastic. All righty. Any other questions? Oh, there's Yuchin has got a thumb up. Or are you there, mate? Yuchin, have you got a question?
I have a question.
Again, your if you
microphone.
Can just microphone.
No, I don't have any question. It's a good strategy to work out with the university and come up with the solution. Very good. Well done, Jason.
No worries. All right. Any other takers? The only thing I'd say, just in terms of papers, Concrete 2025, Concrete Institute of Australia. Yes, it's a slightly different area to where you're in, but your research would be fascinating there, because I think that there's a lot of suppliers there, and there's a lot of engineering designers there. Your information can be very useful and educational to people that are working in that area. The other thing, of course, is from a university sense, you might be working on pipes, but who knows? Your next application for your little gizmo might be a culvert or something like that. Remember, equal number of culverts out there or whatever. So I'd encourage that. But look, thank you so much for everything. It was absolutely fascinating, Jason and Alex, and thank you also for all your comments, those who are on.